Welcome to Brain Vision.
Okay, so in this problem we have three gears. So first of all, let's try to draw the gears in here. So we have the two gears in here and the third one in here. This one is a little bit bigger than the other two. So that's basically our system. Okay, what we know. This is going to be the gear A, B, and C. We know the problem says to us that the mass, let's put here, the mass of gear A is going to be equal the mass of gear B, which is equal 2.4 kilograms. What else do we know? We know that the radius is 60 millimeters. So we have the radius A equals the radius B, that is equal 60 millimeters. What else do we know? We know that the mass of gear C is 12 kilograms, and we also know that the radius of gyration of the gear C is 150 millimeters. Okay, so that's basically the information about the system that we have. We also know we also know that a couple m. So let's put here we have a couple m with constant magnitude of 10 newtons meters is applied to the gear C. And this problem just want to know in the first part, so in part A, we want to know the number of revolutions on the gear C required for its angular speed increases from, let's put here, the angular speed, this is omega 1, goes to omega 2, and we want that omega 1 is equal 100 to, let's see, 450 rotations per minute. So that's part A. We want to know the number of revolutions, so we want theta, the number of revolutions for the speed increase by this amount. And in part B, we want the corresponding tangential force acting on the gear A. So we want the tangential force. Okay, first of all, we know that the three gears has a moment of inertia. So let's put here the moment of inertia of the gear A, which is going to be equal to the gear B because they are equal. And we know that the moment of inertia is just mr square, which gives us 2.4 that multiplies in meters 0.06 square. Okay, that gives us a total of 8.64 times 10 to the minus 3 kilograms meters square. So that's the moment of inertia of the gear A and the gear B. Now let's do the same for the gear C. And the moment of inertia of the gear C is the same equation, so it's just 12 that multiplies the radius, which is 0.15 square. That gives us a total of 270 times 10 to the minus 3 kilograms meters square. Okay, That's the first thing we must know, the moment of inertia of each one of the gears. But now, in order to calculate the part A, we want to know the number of revolutions to the speed increase. And to calculate this, we must use the conservation of the energy. Let's put here on black. We must use the conservation of energy. Therefore, we know that the kinetic energy of the system in the first position plus the energy generated by the couple to go from position 1 to position 2 needs to be equal the kinetic energy in position 2. Okay? Therefore, we must calculate each one of these quantities, and there, and after that we will find the answer for part A, which is the number of rotations. So first of all, who is the kinetic energy in the first situation? Is just the kinetic energy of the gear A in the first position plus the kinetic energy of the gear B in the first position plus the kinetic energy of the gear C in the first position. And that's just, let me see, half of I that multiplies omega. Let's put in this way. This is just half that multiplies IA omega A plus IB omega B plus IC omega C. Okay, but how we going to, we already know what is the values of the moment of inertia. We just calculate this here. But what is the values of the angular speed? Okay, we know the angular speed of the gear C. First one needs to be 100. Okay, therefore let's use the kinematics theory, and we know that let's put here another color. We know that RA omega A needs to be equal RC omega C. Therefore, we can say that omega A is just RC omega C divided by RA. And that gives us a angular speed of, let me see, 150 divided by 60 omega C, which gives us a total of 2.5 omega C. And that's the correlation between omega A and omega C. Therefore, in the first position, what we're gonna call omega A1 is going to be 2.5 times 100, which gives us a total of, let me see, 25, 250 actually, 250. Okay, rotations per minute. Okay, so that's the value of omega A1, which is going to be equal to omega B1. And now we can calculate the kinetic energy in the first position. Let's just make one observation here, that we do not want to calculate our energy in rotations per minute. We want in radians per second. Therefore, this is going to be simplified. Let's put here an arrow. This is going to be 25 divided by 3 pi rads per second. Okay, and that's the speed that we're going to use. So we just need to substitute the numerical values in here, and we're going to find that K1 is just After using uh, these values that we have for the moment of inertia, A, B, and C, and the value for the speed, we will find that the kinetic energy in the first position is going to be equal 20.726 joules. Okay, so that's the energy of the first position. In the second position, well, in the second position, let's make a division here. We again need to use the same equation, but this time we substitute the ones for twos. And again, we're going to see the same problem with the angular speed. We need to find the angular speed of the gear A and the gear B. And we're going to use the same calculation. So let's do it here. We know that the correlation between omega A and omega C is given by this equation here, 2.5 omega C. And in the second position, we will have that omega A2 is going to be 2.5 that multiplies 450 rotations per minute. This gives us precisely, let me see, 37.5 pi rads per second. And that's the omega that we're going to use. Therefore, the kinetic energy and point in the position 2 is going to be equal half of moment of inertia of A omega A. We can multiply by 2 because it's equal to the moment of inertia of B plus the moment of inertia of C omega C2 and 2 in here. I forgot to put this index. So calculating this is the same moment of inertia. The second speed is the 450 that we want to calculate, 450 rotations per minute. Therefore, we find that the kinetic energy at the position 2, let me see, is going to be 419.7 joules. That's the second kinetic energy. And finally, but not last, we need to find the potential energy of the couple that moves the gear for position 1 to position 2. And that's given by the magnitude multiplied by the angle of rotation of the gear C. And the magnitude, as we saw at the beginning of the problem, is just 10. Therefore, this is going to be equal 10 theta C. And theta is precisely the answer that we want. Therefore, solving the equation for part A, so part A, we have to solve K1 plus the energy, potential energy from position 1 to position 2 plus K2. So that's going to be equal 20.726 plus 10 theta C equals 419.7. That gives us a value, let's put here, of theta C equals 39.898 radians. Therefore, since we want to discover the number of revolutions that the gear C must do to generate this speed, to go for this speed, we just need to divide it theta c by 1 revolution, which is 2 pi. Therefore, we will find that the number of revolutions is going to be equal 6.35 revolutions. And that's the answer for part A. We still have to answer the part B. And what do we want in part B? Let's remember here, we want the tangential force on the gear A. I forgot to put this here. We want the tangential force on the gear A. Okay, how we going to calculate the tangential force? Well, to calculate the tangential force, we must remember that this is just, let's put here, the tangential force is just going to be the magnitude in the gear A divided by the radius of gear A. This is the definition. Therefore, the only problem here is to discover who is the magnitude on the gear A. So, to calculate this, we will use the same equation we used to calculate the part A. We're going to use the kinetic energy, the principle of work and energy. Therefore, let's do it here. The principle of work and energy for only the gear A, we are not looking to the entire system anymore, only for gear A, K1A plus MA theta A equal K2A. We already know what is K1 and K2 because we already calculated this. It's just the moment of inertia multiplied by the speed, the angular speed square. Don't forget this. I actually forgot to put this here. The angular speed square. Here we also have the angular speed square. Sorry guys for forgetting this, but we need to put this square, otherwise this will be incorrect. Let me see. K2 on the gear A. Okay, so K1 and K2 we already have. This is going to be 2.6909. Actually, no. 9609. 9609 plus MA that multiplies theta A, that is equal 59.957. Okay, so who is the theta A? Well, let's use the correlation between omega A and omega C, but instead of using for angular speed, we're going to use for the rotation. Therefore, we can say here, let's do the observation, that theta A is 2.5 theta C. Therefore, theta A is going to be equal 99.744 radians. Therefore, if we put this value in here, we will find that the magnitude is going to be equal 0.0 57,142 newtons meters. Okay? And finally, our tangential force is going to be equal 0.57142 divided by 0.06, which gives us a total of 7.14 newtons, and that's the value of the tangential force on the gear A. Okay, that's the final answer. Thanks for watching.